Let us take a look at another example where we will see that it is possible that we may not associate dual variables with all the constraints. In other words, we can say that we may not dualize. Dualize means associate dual variables, all the constraints. So it's not necessary that we associate dual variables with all the constraints. For this, we will now take a very interesting example. We will consider a difficult problem. So we will consider minimize C transpose X, Ax less than equal to B, and Xi is either 0 or 1. Note that this is an integer programming problem. A general integer programming problem is said to be NP hard, which means that there is no algorithm which can solve a general integer programming problem in time that depends polynomially on the dimension. So here X is in Rn. So generally all algorithms that solve it in a guaranteed fashion require time which is exponential in n in the worst case. Right, so this is a genuinely hard non-convex problem. Let us try to find its dual, and remember that regardless of what the problem is, the dual is always a concave objective and convex constraint, so convex optimization problem, and therefore the dual can always be solved, and we'll see that here. Now to do that, what we will do is that we will not dualize this constraint. In other words, what we are saying is, let us define this function f of x is equal to C transpose x for all x such that xi is in 0 or 1. So I'm defining this function. You could say that the domain of f is the all n-dimensional 0, 1 vectors. So that is the domain of f. So this way we can write the same problem as minimize f of x subject to ax less than equal to b, and x is the optimization variable. The only thing hidden in f is that the domain of f is non-convex. So therefore f is not a convex function because its domain is non-convex. So if we write it like this, let us associate a dual variable lambda which is in Rm. So let's say that A is in Rm cross n. So lambda which is in Rm with this constraint. So then the Lagrangian is given by L of x comma lambda equal to C transpose x plus lambda transpose Ax minus b, because the constraint is Ax minus b less than equal to 0. So we have this as the Lagrangian, and we are emphasizing that the domain of L is given by 0, 1 vectors of size n cross, so the domain with respect to L is lambda greater than equal to 0. So R m plus. So this is the domain of L. Now let us call this as Bn. So this is written as B of n times R m plus. Now the dual function is given by g of lambda equal to minimize x over b of n, and the objective function is C transpose x plus lambda transpose Ax minus b. Now let us massage this a little bit, because observe here that the objective function depends on xi's, and each of these xi's appear as a summation, and likewise in the constraint. So let us write it as minimize x in Bn and C plus A transpose lambda transpose x minus B transpose lambda. So I've separated out the terms that depend on x and separated out the terms that are constant with respect to x. And now let us solve this subproblem. So let us solve this subproblem. This subproblem, essentially you can observe that you can write it as minimize xi in 0, 1 summation over I equal to 1 to m c plus A transpose lambda ith entry times xi. So we are multiplying the ith entry of this with xi, summing, and that is the objective function. And this objective function is separable in terms of xi and the constraints also. So therefore we can interchange the minimization and summation. So the summation goes outside now, and the minimization is with respect to xi now instead of with respect to all x. So this is minimization, and then the objective is c plus A transpose lambda I xi. So now the summation has gone outside. Now this problem is relatively simple to solve. Let us solve this problem separately. So let us write down minimization of hi xi, where xi is either 0 or 1. So you already know how to solve this kind of problem. Essentially we are minimizing hi times xi. We will pick xi equal to 0 whenever hi is greater than equal to 0, and we'll pick it to be 1 whenever hi is less than equal to 0, so that hi times xi is as small as possible. In fact, in this case, hi times xi will become 0 whenever hi is greater than equal to 0, and it will become 1 whenever hi is less than equal to 0. So this is, sorry, it will become hi when hi is less than equal to 0. So this can be written as hi comma 0, minimum of hi comma 0. So therefore, applying this formula here, we will get this term as summation over I equal to 1 to m minimize c plus A transpose lambda times ith term comma 0. So the minimum of these two will be what we are getting. Then the dual function is given by g of lambda equal to minus B transpose lambda plus summation over I equal to 1 to m minimum of c plus A transpose lambda I comma 0. So this is the dual function. Let us now write down the dual problem. So what is the dual problem? We have maximum over this objective, so minus B transpose lambda plus summation over I equal to 1 to m min of c plus A transpose lambda I comma 0, and subject to constraint lambda greater than equal to 0. Let us simplify it a little bit. We have a maximization problem, but one of the objective is the minimum of two terms. So what we can do is we can apply the epigraph trick, but in the opposite direction. So this problem can be written as maximization of minus B transpose lambda plus summation over I equal to 1 to m. So this is with respect to lambda. Now we introduce another set of variables. So maximization of this subject to the constraint that minimum of c plus A transpose lambda ith value comma 0 is greater than equal to ti. This is the opposite of the epigraph trick. You can call it hypograph trick. And lambda greater than equal to 0. And further, this constraint can be written as c plus A transpose lambda greater than equal to t, because minimum is greater than equal to t means both are greater than equal to t, and 0 is greater than equal to t. So these are the three constraints now, and this is the objective function. So what can you say about this problem? What kind of problem is the dual problem? You can see that the objective is linear in lambda and t, and the constraints are also all linear in lambda and t. So this is therefore an LP. So we have now seen that we started with an integer program and we calculated the dual and we got a linear program. And further, if the primal objective is P, then it is greater than equal to the dual objective, which is calculated by solving this linear program. We already know that linear programs can be solved very easily. So therefore, for any given integer programming problem, we can quickly find out a lower bound on the objective. And in fact, this method of finding the lower bound quickly using the dual problem is very useful in the context of integer programming algorithms. A lot of integer programming algorithms, such as branch and bound, rely on this method. So they use this method repeatedly and try to refine or try to focus or narrow down on one particular solution by repeatedly calculating lower bounds using the dual formulation of modifications of the original problem. So in this example, we have seen that we can obtain a dual formulation, and there are different options available to us whenever we are dualizing the constraints, and we may choose not to dualize some constraints also. If we don't dualize some constraints, then those constraints would have to be handled during the minimization of the Lagrangian. So if we go back, you can recall that if we do not dualize some of the constraints, if we put them in the domain of the function, then we will not be required to dualize them, but they have to be handled during the minimization of the Lagrangian or during the calculation of the dual function. If we do associate dual variables, then we don't have to worry about them. So it is really a matter of choice, and you will see that the formulation, dual formulation, will actually depend on what choice we make, whether we put the constraint within the domain or we associate dual variables and convert it into the dual formulation or include it into the Lagrangian. And the corresponding dual problems will oftentimes be different, and we may choose one over the other depending on the scenario. Sometimes one of them may actually be easier also. So we are done with weak duality now, and next we will proceed to strong duality.